Question number 3.188. In this question, a circuit is given, comprises of one EMF E. There is a switch. After that, one capacitor is connected here and two resistance of equal amount, resistance R and resistance R are connected here. Okay. Now the question is stating that find the voltage, find how voltage across this capacitor, this voltage, is varying with the time when switch is closed at the moment t equals to 0. It means in this case switch is closed at very moment t equals to 0. So it means this circuit is closed now. And now we need to analyze this circuit. Okay. So let's assume why this condition is given t equals to 0, because when t equals to 0 is given, just closing the switch, then this capacitor will respond to the circuit. Okay. But if this time is too long, then steady state will occur and capacitor will block the further flow of current. Okay. That's why we are doing this analysis as t equals to 0. Right. Now see. In this case, here you can see, if we'll assume that let charge in capacitor is Q, then the potential difference across the capacitor would be Q over C, right? And here we can consider that suppose current I1 going through this resistance, okay, and current in this circuit would be through the capacitor would be dq over dt if charge is I, right? So we can establish two relations. First, this resistive element is connected in parallel with the capacitor. So in parallel combination there are same potential. So voltage across capacitor at any instant would be equals to voltage across the resistance, that is I1 into R. The very first equation. Second, current I1 is coming from this resistance and dq over dt, I2 is coming from the capacitor. Then according to Kirchhoff's current law, the current passing through this resistance would be sum of incoming current. So here this I can be written as I1 plus I2, which is equals to I1 plus dq over dt, right? And so if we'll apply KVL, okay, Kirchhoff's voltage law in this loop, or you can apply in outer loop, as those two elements are in parallel, so there will be no effect. So let's take outer loop. Okay. So now I am writing that applying KVL in outer loop. Let's take loop number 1, this path. So here you can see we have applied total EMF E, right? And there is a potential drop across this capacitor, that is Q over C minus Q over C. After that, there is potential drop across this resistance, that is R into I, and it must be equals to 0. As Kirchhoff's voltage law suggests, that total voltage in a closed loop is equals to 0. So from here we can write E is equals to Q over C, right, minus R, in bracket we can write I1 plus dq over dt. Okay, if we'll replace on left side, or we are not doing any transformation. Now see, if you open this bracket, then we'll get another term R into I1. And from equation 1, this is equals to Q over C. So from here we can write E minus Q over C and Q over C for this term, 2Q over C minus R dq over dt is equals to 0. Okay, so we can further rearrange this expression. Then we can write dq over dt is equals to, or R into dq over dt is equals to E minus 2q upon C. Okay, or we can say dq over E minus 2q upon C is equals to dt over R. So we can integrate this term. Okay, and assuming that when at very initial moment there was no charge in this capacitor. So from here this term, integration for this term is T over R. For this term you can take E minus 2q over C as any variable, dummy variable x. Okay, and from there we'll get minus 2 by C dq is equals to dx. So we can replace this dq as dx into C by 2 with negative sign. So from here we'll get C by 2 with negative sign, and this is dx over dx, so we'll get limit ln x. Okay, and if we are replacing that E minus 2q over C as x, so when q is equals to 0, x is equals to E, and when q is equals to q, then x is equals to E minus 2q upon C. That is equals to T upon R. So from here we'll get C by 2 ln E minus 2q upon C upon E is equals to minus T over R. Right. So this term can also be replaced on another side. So from here we'll get ln E minus 2q by C over E is equals to minus 2t over RC. Okay. Now we can eliminate this term of ln as exponent. So this is E minus 2q over C is equals to E into exponential minus 2t over RC. Okay, so from here we can write 2q over C is equals to E, and we can take this term on this side. So 1 minus e to power minus 2t over RC. And this q upon C is voltage at any instant stored in capacitor, what we are trying to find out. Okay, so V is equals to 1 over 2 into E, 1 minus e to power minus 2t over RC. This is our final expression for change in voltage across this capacitor with respect to time.